Yeah, now we finish with the white paper, the Ethereum white paper. Let's move on to the yellow paper, which is going to be about the implementation. So the yellow paper will have much more details than the white paper. And it's also much longer. By taking a quick look, it has nearly 40 pages, and it's a formal specification of Ethereum. We are not going to read line by line. I mean, I'm not going to read out line by line like the white paper, because that would take way too much work. And actually, I think that we can safely skip over quite a lot of content, since our goal is not to implement full Ethereum client. So with that being said, let's get started. Introduction. Okay, what's about introduction? I think after reading the white paper, where we can skip over the introduction and go to the blockchain paradigm. So what it says here is that they define formally the state as being sigma t, and that the transition between one state and to the next one is through the Ethereum state function, which this character, I don't know what's the name of this character. Okay, and that it's the only parameters are the current state and the transaction. So I look up that character, and I think it's gamma. And then transactions are put into blocks, and blocks are chained together using a hash, and therefore they form a journal. So a journal is in computer science is a set of transactions that have to be executed one after another, and it records the history. So sometimes it's called a log. They also mention that the state is not including in the block, because it would be way too big, but the state is implied. I mean, you have to maintain a state, and there's a official canonical representation of the state that is put into the block. Then you have the idea of mining. So mining is putting some work into finding particular value that makes the block acceptable. So here it's about hashing the block header and getting a value, output value, which interpreted as an integer would be enough to say that this is a valid block. Then there's this formula about how you represent this. So B is the block. B is the block. Let me see. Yeah, B is the block, and you apply. So you apply this particular sigma sigma. Yeah, sigma. Is sigma? Pi. No, it's pi. Sorry. Pi function on the block, and the block is something, but mainly the block is a bunch of transactions, and that sigma function is the application of the gamma function, which changes the state incrementally. So from t0 to using t0, you start from little sigma 0 to sigma 1, and then you apply t1, you get sigma 2, and so on and so forth. So you have to apply this gamma function for each transaction in turns. And finally, there's a gamma function. There's a sigma function, which finalizes all the changes, because the transitions on do not include things like the reward. So, and from a macro perspective, the big sigma is the result of applying all these transactions and the finalization function on the state. So the little thing here is that sigma t is it's not exactly the same as sigma t here. The sigma t here is for one transaction, and this sigma t here is after the block. Then it talks about the value, so just the names that have been officialized, the weights above in the game, and Ether. So it's worth noting that Ether is quite large. It's 10 power 18 Ether. In Bitcoin, it's only 10 power 8 Satoshi. Thing about history. So history, it's a summary of what was stored in the white paper about what happens when a fork occurs. A fork which naturally occur, not talking about changes in the protocol or attacks to the network, but a fork would appear when two miners manage to solve the same block at the same time. So since the hash value that can hash values that can be acceptable for block are quite numerous, it's and the difficulty is much lower than blockchain than Bitcoin blockchain, since the target is 10 seconds per block. It's more likely to have several miners finding blocks that are valid. So in which case a fork occurs, because there's no block that is better than the other in that case, and they will exist for some time until there is one that gets extended by another miner. So they extended the Bitcoin validation protocol with Ghost, which also rewards the uncles. Then there's a bunch of like writing conventions. I think we can skip that. So we have to remember that they have okay, I think we can read this very quickly. All right, so world state. The world state is the entire state of the Ethereum. So this is actually the world state, this sigma t. And it's so you take each address. So the key of Ethereum data model are addresses, not UTXOs, not transaction endpoints. So addresses and the state of that account. So an address is a key for an account, and the account state is the data associated with our account, and that account state is serialized or written as bytes in a special format called RLP, and this is defined in Appendix B. So I think we will reach that eventually. That state is not stored on blockchain, but you must follow a particular implementation, which is this Merkle Patricia tree. So that would be very interesting to see, because the hash of that particular, the root node of that particular tree will be stored in the database, will store in the blockchain, and the tree can be stored as key value pairs with a mapping between byte arrays to byte arrays, which is convenient because they are well-known implementation of such a database. So this is not really like it's not a SQL database, because you can make queries besides looking up a value by key. But we have efficient implementations of such a primitive low-level database, and pretty famous one is LevelDB. It's from Google. Okay, so advantage of this is that the root node is put in the blockchain, we just mentioned that. And second is it's an immutable data structure. So whenever you insert, change, or delete a value, you are going to create a new state, a new node somewhere, and there will be still a way to reach the previous state. So it's the entire history of the state, of the world state, can be recovered. So one of the questions is, of course, that if that's the case, how long are we going to keep all the states from Genesis, in which and if so, would that be too large? So is there a pruning mechanism to remove states that are very, very old? So then it defines what's the account state. So this is also should match what we learned in the white paper. So we have a nonce, we have a balance, we have a storage root. So it's a bit different, because we knew that the storage was so this hash was also a key value pair mapping per account. But now we know that is also organized as a Merkle-Patitra tree, which actually makes sense. And that root of the tree is in the account state. Then we have a code hash. So the code hash is a hash of the code if it's a smart contract account. Okay. So this says that this stuff cannot change. So smart contract account cannot change. If you change the code, that code hash will change, right? Nonce will increment, balance will change, of course, if you send or receive money, and storage root will change if you change anything in the storage. Okay, so the code is written like that. That hash is written like that. Okay, so some notation here. If it happens that your account has no contract, then you still hash it, but it's a non-result, and this will be an externally owned account. All right, so more notation. Okay. This is a validity function. See, the count is valid is if all these values are in the right set. So xn, where it was x. Okay. Xn would be nonce. Okay, so it's saying that the nonce must be an integer, balance must be a positive integer, and these hashes should be 32-bit hashes. And then account is empty, no code, no code, no nonce, no balance. Okay, there's also the notion of a dead account. So what's a dead account? Or empty. So there's no state, or the stuff is empty. So to be empty, okay, whatever. Transaction. Okay, so transaction is important. We have a nonce. So when you send a transaction, you need to send a nonce that matches your own nonce. So that means that if you send a transaction twice, it will have a different nonce, and therefore it will be hashed to different values. So even if you upload, if you deploy the same contract several times with the same data, and from the same account, you will still get a new address because the transaction will be different. That part I'm a bit clear. Transaction will be different, that's for sure, but whether it's a different address, I think that will be the case, but let's just verify that. Then you have a gas price, gas limit. They call it start gas before, but that's gas limit now. This is a recipient. This is the value that is transacted. And then you have a signature. So we have three terms for the transaction, for the signature. RS is probably the DSA signature terms, but V I don't know what it is. Okay, let's see. It's appendix F for that. And then you have. So you have also, this is new. You can also pass some byte array to pass some initialization code. Init is an EVM code fragment. It returns the body, a second fragment of code executes each time the recurrence of message call. This is for the basically this is for the contract creation. So contract creation is a bit different because you will be sending this transaction to a particular address. Okay, so to create a contract, you need to send it to the MP address, it's B0. So you're sending to address that has 0 everywhere, and then you pass some init code, and that init code will become the body of your contract. Then afterwards, if you want to send call the contract, then you have to pass data. Signature use ECDSA. Okay, so transaction will have all this if it's transaction contract creation, and all that if it's not. So we have nonce, price, gas limit, gas, T2, okay, all these guys, right? And then all these stuff are serialized with this format, and it must be part of this set. Okay. Okay. Now the block. So this is very formal definition, but it's actually really matching the stuff on the white paper, except for they talk about gas limit is start gas in the white paper, but start gas here, and then there's a term about the signature, more formal, and there is we know that they are sending to address 0 for the contract creation. Now the block. So the block has a header, a set of transactions, and a set of other block headers. So these are the uncalls, right? Yeah. They call them as omers. Okay, so what's omer? Okay, there's a note about what omer is. I think omer is like uncalls, but Anyways, the header has a parent hash, so this is the link to the previous block. That's why we have a blockchain. Almost hash, so we hash also these guys. Beneficiary, this is the guy who mined. State root, okay, so this must be the hash of the state tree. So the hash of the dispatcher tree. Transactions root, so this is the Merkle tree for the transactions. Receipts root, okay, what's receipt? Receipts is the return value basically of the transaction. Not technically the return value, but once you make a transaction, you get a receipt. Logs bloom. So the bloom filter composed from indexable information. Okay, so this part we don't know about. This is new. The difficulty, this is where the current difficulty for the proof of work. So this is the block number, gas limit for the entire block, gas used by this block, timestamp, extra data. So you can put any value you want in block. Mix hash. Uh, 256 hash will combine with the nonce prove that a sufficient amount of computation has been carried on, formally HM. Oh, this is the stuff that you put in order to reach the to do the proof of work. So, but then we define what this is, right? And the nonce. Okay. The other two common blocks are simply list of almost block headers. So that's you, right? And the list of transactions. Transaction receipt. Okay, so the two things we don't know is transaction receipts and logs. So when you run a transaction, you execute it, and this is going to show that this should be usable to show that you have actually executed the transaction without running it. Okay, so you need to put the gas used, the logs, the bloom filter, so this is R used, this is the logs, and this is the bloom filter, and the status code. Okay, so we are still don't know what's the so now we know what's the receipt. So nothing special. We need to know what the logs bloom filter. So serialize all that stuff, and we must have a result that is a byte. Right? Alright, the sequence are RL, so then finally we have this guy. A series of log entries. A log entry is the tuple of the log address, a possibility string of log topics, and some number of bytes. So this is something that we should be able to generate from the code. So we should be able to emit to create a log entry, and then all these log entries will be put serialized, and then we have a bloom filter. So the key to this log entry for the bloom filter is okay. So the bloom for the reminder, right? The bloom filter is a data structure that allows you to figure out if the entry is present. So it's not guaranteed to be a one-to-one mapping. So if you're asking for a particular key, it can answer yes, it's there, or yes, it may be there, or no, it's not there. So it's you can get a positive, negative, positive no. But if the Bloom filter replies yes, then you still need to look up more precisely. So it's more like a pre-filter. So a Bloom filter is allowed to have collisions, basically. It does this through taking a low order 11 bits of each of the first 3 pairs of bytes. Okay, so this guy here has 3 terms, right? It has the address and a series of topics and the data. So three components. Then you hash each component with this Kersec 256, and then you take the 11 bits out of these 3 parts, and then you get that particular key to that Bloom filter. So again, the Bloom filter here is to be sufficiently random, or not like random, but it has to be deterministic on the input, of course, but sufficiently equally distributed, so that it uses efficiently uses its bits. Okay. And now about the validity of that block. So so just formalize what's the okay, so we can skip that. And now talk about serialization. This is all about the format of the header and the blocks. Okay, block header validity. I have to go faster, so it's page 6. Oh, there's a formula about how you calculate the difficulty. So this is a formula that gets you the minimum hash value. So this in part is actually interesting because they mentioned something like difficulty time on or ISH. So this was something I read earlier, where they wanted to fix the difficulty so that people would sensitize the mind, and then make it rise quickly afterwards. But they didn't go through it. Okay, this doesn't really matter to us because we are not implementing the whole thing. Okay, the mixed hash will be interesting to understand though. So understand the nonce. Okay, let's go back, see what's the mixed hash. Oh, the mixed hash is that you need to hash the DAG being the what do you refer to DAG actually? DAG. Yeah, they just mentioned DAG here. Okay, so I think this refers to the white paper where they say that in order to calculate the Ethereum hash, they want to include a large portion of the data, so that as a miner you need to have a full node and not just rely on the header. So they want you to prove that you're not gonna use. I mean, they're gonna prevent ASIC and dedicated hardware to be miners. So you need to provide a mixed hash and the nonce. So they're both gonna be verified. And mixed hash will be proving that your work is well, I'm repeating myself here, but the work is sufficiently difficult to do. So for example, you will use a lot of memory and sufficiently random that you can't use dedicated hardware. You need to have a CPU, but they actually don't mention exactly what's the DAC here. Maybe later. That's something they should have mentioned. Okay, the gas and payment. So there's a gas limit. So there's a schedule for paying, the fee schedule, and the gas limit, gas price. Okay, gas limit will be the remaining will be returned. In general, Ether used to purchase gas that is not refunded is delivered to the beneficiary address. The address of the control the miner. Okay. So you pay the fees to the miner. Okay. Execution. So that's the model for execution. This is the same as before. This is self-destruct functionality. What's that? So you have to pay for the transaction creation and you have to pay for the transaction cost. Okay. 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 Well. So you can call a function of code that basically destroys your contract. Okay, it's not very interesting here. Contract creation. Endowment. What's endowment? Alright, so I have to get this address. So being the rightmost cache address LLP encoded instruction containing only the sender and the account nonce. Yeah, so it's the sender and account nonce that defines the contract hash. And now they have a new rule. Okay. They're sorting it. Okay. So they make it even more different. So you have some initialization code, but that initialization code is then discarded. So that means that if your code has some kind of constructor, then the constructor actually will not be part of the code deployed. That's interesting. It kind of makes sense because that initialization code will set up your contract state, but since it's meant to be used only when the contract is deployed and never afterwards, there's no purpose in storing it and wasting space in the state. Okay. Now we have an out of gas situation. Deposit. Okay, talking about you have to pay anyways. Alright. No subtleties. Okay, message call. So message call is when you call one contract from another contract. So actually I have a question here, but I don't know if it's going to be answered. Is what if you're calling a function that does not change the state? Like many of these functions, like for example, you're using this name registry thing, and you want to know who owns a particular address or who owns a particular name, and you have these smart contracts that keeps track of that in its storage. So your contract which should have also the ability to query who's the current owner, but you need to pay gas for that, because technically you could run that function locally. You don't have to go to the network, since if you have a full node, your full node would have the state root, the state tree, and you could do this calculation or this computation locally. And I don't see why I would have to make the network pay or pay something for something that the network doesn't have to do. But I don't know. That would be kind of bad to have to pay for that. I would not be happy. So let's see. No, but that's not about it. This is about delay get call. Okay. Alright, delay get call is just like a nested call. Okay, but not super. Why is this guy different? What are we talking about here? Okay, so they do say that if you're calling to a nested function and it has an exception, then you revert to your state prior to calling the function. So it doesn't unwind the call stack by one, not the entire stuff. And what is this table here? One event equals one. Okay, I hope you explain that. Oh, okay, there are some contracts that are considered pre-compiled. The 8 contracts in address 1 to 8 execute the elliptic curve public key recovery function. The SHA, the REPNI, the defunction. Okay, so there are like 8 contracts that are half coded. This one is what? It's not kidding. Okay, this is I don't know about this one. Elliptic curves elliptic curve pairing check. Okay, I don't know about that one. It's in the appendix E. So execution model for the EVM, this it's a stack-based thingy, a stack-based virtual machine. Right, and it has so it pays fees. Okay. Alright, address account on the code, selection, price, byte array, data, address account, value, byte array, def, okay. Only page 12, man. Okay, it's just a form. This is a formal definition of what they said earlier. So it has, the important thing is in machine state. Machine state. So it has memory contents and the stack contents. So the memory contents, you also have the how much memory you have used. This is error. Drum destination. Okay, you cannot jump anywhere. You have to jump to code. Execution cycle. Okay. Let's go here. The blockchain. The canonical blockchain is a path from to leave. Heaviest path. Okay, this just say that the longest chain is the chain that has the most the highest total proof of work. It's a sum. So when you finalize a block, you validate the omers. You need to validate the transactions. The rewards apply, and then you do the nonce verification. So the omers verification. So it's interesting because omers, they just have to provide a header. They don't have to provide the transactions. So yeah, you just need to validate that the block header is correct, but the content of the content of the state root and all these hashes, since you don't have the transactions themselves, you should not have to verify it. Okay. All right. Reward. So this formula about the you get some part for the omers. And then there's a validation of the state root. Okay. Forward. Classique, ouais. Okay, so talk again about the mixed hash component. They still don't say what is D though. Okay, the hash. I think they really don't mention what's D. Don't know how you can implement that without knowing D. So Ethash is Okay, some definition of the hash. The interesting thing is that the hash requires data set, and data set is large. Okay. Okay. Is it yeah? Oh, now we get the appendices. All right. Let's see. Yeah, this is RIP. So this is how they serialize stuff. So it's probably gonna be tedious, but it's about how you serialize the integers, byte arrays, nested structures, stuff like that. Yeah. So that ignore that. Or the hex prefix encoding. This is a byte array encoding. So okay, so part should also part of RNP, no? Okay, the Patricia tree. This one should be interesting. Okay. Okay. Okay, this is the part where this is how you build a radix tree. A radix tree and Patricia tree is the same thing. Okay. Okay, this is new extension. Okay. Okay. So what's the extension for? They don't explain why you have this extension. Okay, we need to read at something more detailed than that. Okay, that's okay. There's these pre-compiled contracts. Okay. Oh, okay. They should provide two values, and because when you do a zk dark, you have to have these two large primes, and they are related somehow. The thing is that normally you generate something random, and then you derive these two values, and you have to promise that you destroy the source. It's like having public keys, not having a secret, and promising that you destroy the secret. So, okay, this is elliptical math, and that can be used to verify zero knowledge proof. Okay, when you sign transactions, okay. This is the standard signature with and when you sign, you actually have two valid signatures, and they choose which one you should send, the positive one. Now you have a fee scheduler, so every instruction would have is going to be assigned a value. Okay, it's not so long actually. So what's the most expensive one? Create is expensive. does this thing here? That must be. Alright. Then there's a spec of the. So all these instructions, right? Yeah, all the instructions are going down. Alright, so this is definitely not going to be for us. And then there's some bugs. Alright, so that is it for this. Our questions were not, my questions were not completely answered. So one was how does the partition tree work? Is there any pruning of the data, and how you can make it persistent and a Merkle tree? So I guess we're gonna have to find another explanation. Second is for the smart contracts, do have to pay for the functions that do not change the state. And the third one is actually, I think it was answered. Is well, no, it was not really answered. But the what is the mixed hash, the stuff that you're supposed to use to do this mixed hash? So I'm gonna put like a summary of these three questions, and we'll look for answers.